Okay, so I will start the review session for this midterm 3. So I will give one full problem. I will solve one full problem, and then I will give a hint for several problems and topics that we covered. So let's start by this one. Now, as I mentioned, just to remind you again, the exam will cover chapter 27, chapter 28, chapter 29, and then the inductance will be chapter 30. It will be this optional question, an optional question, which will be given on chapter 30. So let's start by this problem. Okay. So here we have a conducting loop of radius 3 centimeters is placed in a region of a magnetic field that is equal to -AT, where T is the time in second and A is a positive constant. The vector area of the conducting loop forms an angle of 60 degrees with the direction of the magnetic field. Calculate the magnetic flux through the loop. What are the direction and magnitude of the induced EMF? The loop is made of a copper cable, then calculate the current. Okay? So the first thing is, the most important thing here is to look at the problem itself and what is given. So it is a conducting loop, so the radius is constant, which means the area of the loop is constant. But what is changing is the magnetic field. So the magnetic field is changing, and the magnetic field is changing in a negative direction with negative values. So T is the positive and A is positive and with the negative sign. So the question is calculate the magnetic flux through the loop. So normally if the loop is this, and then the magnetic field is this way, and the vector area has it's more than that, a 60 degree angle. So the magnetic flux is equal to B times A, sorry, the area. And so the magnetic, so it's the magnetic field minus AT, and then pi r squared, and then cosine 60 degrees, which can easily be calculated as 0.014, and then A times T. A is a constant, and this will be in Weber because this is magnetic. This is magnetic field, magnetic flux. Sorry. Okay. Then the second question is, what are the direction and magnitude of the induced EMF? Now, why do we have an induced EMF? Because the magnetic flux is changing as a function of time. Now, what is the EMF? The EMF is equal, according to the Faraday's law, is minus the rate of change of the flux, which in this case is equal to 0.0014 A, which is a positive value because A is positive. Of course, the unit is involved, and it can be easily seen that the EMF is clockwise, okay? Because it's opposed to the change of the flux. And then the last question is, if the loop is made of a copper cable of cross-sectional area 0.05 square meters, millimeters, so conductivity of copper is given, what is the current area of the loop? Sorry, what is the current across the loop? What is the current across the loop? Now, what is the current across the loop? The current is the EMF that is induced divided by the resistance, and the resistance is easy to calculate. It's just the conductivity, the length divided by the area, and the conductivity is given, right? So it's L over sigma times A. Sigma is the conductivity, and so the length is 2 pi, the area R, divided by the conductivity, and then the area is pi r squared. Okay, so area is, we already calculated it, and you will find that the resistance is 0.059 ohm, and which will give you the current is equal to 0.024 volt. Okay, so this is the current Yeah, obviously, because you have this A from here. So this is a very straightforward application for this one. Okay, so another thing is the another situation is the following. Let's assume, if you remember what we did now, we calculated the magnetic flux and the EMF for a change in magnetic field. It's the magnetic field that is changing. Now let's assume this. Let's consider the situation where you have a region of a magnetic field, a constant magnetic field. Okay, the magnetic field is inside the page, and let's take a rectangular loop. I will say this loop that has a length of L and the width A, and this loop now is moving with velocity v. This loop is moving with velocity v, and it is going into the direction of the region of the magnetic field. Now, here there are three situations. Actually, there are, well, there are 5 situations. Situation here, it is clear that here there is no magnetic field in this region, so the EMF here is 0. There is no EMF. And the second situation is where the magnetic loop, the rectangular loop is moving partially, is entering the region of the magnetic field. Since it is entering, the area that is covered by the magnetic field, or that is exposed to the magnetic field, will be changing, which means there will be an EMF. So this is situation number 2. Situation number 3 is when the complete loop is inside the magnetic field. Now, the area is fixed, and the magnetic field is constant, so here there will be no EMF. And this is situation number 3. Situation number 4 is when it starts going outside with, of course, the same velocity. Now you can see that the area, again, that is exposed to the magnetic field is changing. So here there will be an EMF. And situation number 5 is when the loop is completely outside. In this case, there is no EMF. So please make the difference between these 2 cases. Now the question here is to calculate the flux in each of these situations. Calculate the flux in each of these situations. Let's calculate the flux in situation 2. Flux in situation 2. What is the flux? The flux is the magnetic field times the area. Now, what is the area that it is exposed? The area that is exposed, I want to make a drawing, a simple drawing. So here, this area that is exposed, okay, is equal to A times this dx. So the area B, the area A, dx. But what is dx? Dx is the velocity times dt, because this is moving with velocity v. So the magnetic flux is equal to B, the area, and then v dt, right? Magnetic, and this is the area. Okay. Then so what will happen is let's calculate the EMF. So the EMF will be minus the derivative of this situation 2, magnetic flux in situation 2, which is minus B A V. Okay. So if A is constant, if V is constant, this will be 0, and then the EMF will be counterclockwise, because this is constant, this is positive, positive, positive. So the EMF will be negative. So it will be okay. So then So situation 3, as we mentioned, situation 3, the magnetic flux is equal to 0 because in situation 3, which is this one, situation 3, so the area that is exposed to the magnetic field is constant, and the magnetic field is constant. So the magnetic flux is 0. So this is one situation I wanted to mention. Of course, you can also have something a little bit complicated. Let's say, for example, I can give you the magnetic flux, which is it will be some mathematical calculations, and now it's not the magnetic field is constant, but now I'm not considering a rectangular loop, but I'm considering a circular loop. Now it's a little bit complicated because the area that is exposed is not really it's not, so you have to calculate this as a function of v and dt. Okay, so the area. So now it's the area of the disk or partial area of the disk. So it could be a complicated scenario here, but the same concept. In this case, there will be an EMF, but if the loop is completely inside, there is no EMF induced because the area that is exposed is constant and the magnetic field is constant. Okay. So another situation or another topic is the one that we covered yesterday in the review session, is when you have the electric current. So two wires, for example. So this is I1, I2, and the idea is, for example, is to calculate the magnetic, the total magnetic field at a certain point here. Okay, so here it is easy because then you can it's on the same line, so you can easily see that the magnetic flux or field produced by I1 is in this direction. Okay, and yeah, so the magnetic yeah, so the magnetic flux, sorry, B1 should be, this is B1 and this is B2. Okay, so this is B1 and this is B2. Okay. So B1 is inside the page. So if you try to rotate, it will be B1 downward, and I1 is outside the page or out of the page. So B2 or I2 out of the page, B2 will be top. We can also do the following. If I have I1 and I2, let's say I have a point P here, for example, and this point, then I can also calculate what will be the electric field, the magnetic field created by I1 and I2. And at this point P, that is not lying in the line formed by I1 and I2. And obviously here you can use Ampere's law. So Ampere's law will tell you that, yeah, this is the magnetic, no, this is the magnetic field created by B1. Okay, and then do this. Okay, I'm not good in drawing. And the magnetic field by B2 is this. And you can calculate the projections of both magnetic B1 and B2. Do it in a clear way. Okay. So here I have, let's say, this is I1 and this is I2. Okay. And then if I want to calculate at a point here, P, then this point, the magnetic flux will be, the magnetic field will be B1. And then you can calculate the angles here, and you can calculate the projection. Let's say this is X axis, and this is the Y axis. You will have the angle or you will have the dimensions, and you can easily calculate this angle and do the projection B1 along X and Y. Okay, and the same thing for for I2. I2, you will consider, yeah, Ampere's law, and then it will be this one. And then again, you will be able to calculate this angle and do the projection B2 and B1. Okay. And that's it. Otherwise, the rest is the same as we did yesterday. So you can, for example, calculate what is the point, let's say I will call it Q, where the magnetic field, the total magnetic field will be equal to 0. Okay, so you take a point from, for example, I will call it Q here. This distance, let's say this distance is A and this distance is B. So the magnetic field created here by I1, the magnetic field created by I1 will be B1. So it will be mu0 I1 divided by 2 pi A plus B. And the other one is B2 is equal to mu0 I2 over 2 pi times B. And then you calculate I mean, you know A, it will be given. So you will calculate the distance B, and you will be able to find the point at which the total magnetic field is 0. Same thing here. You can also find another point. You can try to find another point depending on the strength of the electric current I1 and I2. Okay. Another situation is the motional EMF. Well, not the motional EMF. It's the following situation, which is very interesting situation, and it is also given in recommended problems. Let's assume I have, let's say, this is a loop with 3 sides, a metallic loop, and then I will put another metal here, another bar, and this bar has a length L and has a weight or a mass M, and I will apply a current I. Now, let's assume I have a magnetic field into this direction. So I know that if I in this and B is this way, this rod, this blue rod, will be subject to a force, and this force will be out of the page. So this force will be out of the page. Now, if this rod is not attached, it's not glued to this 3-side black rectangular one, so at a certain point, if the strength of the magnetic field is enough, this rod can be lifted. And if it is lifted, there will be no contact, and then the current will be 0. And of course, it will fall down. Okay. So the idea here, what will be the magnetic field needed to lift the rod? Obviously, you have to go for the gravitational force must be at least equal, or the force of the magnetic field, because the gravitational force is going into the page. If we look from the top, okay. And the magnetic force is pushing it to the top, okay? So the gravitational force must be equal to the magnetic force, which means mg must be equal to I LB, okay? And you solve the problem. Okay? The last part is the optional part, which is the inductor. Now, let's give an example. If I have this, I have this is R, this is R1, inductor L1, okay, and this is R2, and then inductor L2, and this is a resistor R3. Now, let's say, I need to make a switch here. So immediately at t equals 0, S is closed. We know when S is closed, there is no current in inductors. Inductor is very slow to react, which means the current, the circuit will be equivalent to this. This is the EMF or the battery, R, and then only R3. The others will be open circuit, okay? And obviously you can calculate the current. So the current will be, or I, because there is no change. The I will be just E over R plus R3. Now, if T is sufficiently large, then obviously the inductor will behave like a line, because there will be no charge. It will be completely charged. So, and then the circuit will be just EMF, and then R, and then R1, R2, R3. Okay. And yeah, so I think that's it for this part.